Okay, today's lecture starts the main part of this course, units 2 and 3 together, and takes us back to the 10th century. We're going to derive the equations of motion for this ghastly machine that was part of the culture. And well, actually it goes back 3,000 years if you count the Chinese. The thing that we call a trebuchet, and I spell it out here. It's a French word which means stumbling about, sort of tripping around, and that's what a trebuchet looks like when it operates. So I guess that's my guess for the etymology of that word. In case I first got interested in this because of a Scientific American article in 1995 in which some British people built a fairly large one. And since then, as you can see in some of the pictures down the line there, there have been a number of attempts to recreate situations that were, well, a civil war in England involved the siege of Kenilworth Castle. This is another castle that's sitting on the another Scottish lake, and the battles between the Brits and the Scots are legendary, and involve this machine, this throwing machine. And just to point out that this isn't just about war. This machine duplicates or is analogous to virtually all the human motions of throwing and sports. So we're going to emphasize that a little bit today, but later on when we get quantitative, we'd like to show you a couple of things to prove. If you play golf, prove your golf swing. Play tennis, prove that. So this physics is right here waiting for us to look at. But I should warn you, this is a mechanical problem that has no analytic solution. It's a totally chaotic system in most of its parameter space. So we'll be figuring out various approximations after we rederive all of the stuff that we've really kind of already done. We'll do that today with this real mechanical problem. And the algebra and all of the stuff that we talked a little bit about before will be done again, only in a setting that has a few little extra things that you need to know how to work the Jacobians and the metrics. So let me go ahead here and just point out first of all that the simulations for this thing are right here, waiting to be used on each page, but this is a listing of them that TC has made just by going through and getting them in the right order and making some new ones. The basic idea here for this device, and I will just go ahead here very quickly and do a low-grade simulation. Now go ahead and do it in the middle frame here, just so you can see it easily. The basic idea is this. Let's get the thing running here. Something weird going on here. Did I miss that?
I can't even feed the address in.
Try again. There we go. So that's the basic idea of this machine. And I guess we should do a demo, a real demo. This is the world's probably worst trebuchet, and that's good because it won't hurt you. But what I'm going to do here is I'm going to shoot it, well, sort of in your direction, but as I say, it's a pretty terrible setting for not getting much in the line of speed and range. But let me go ahead here and roll this thing back, and I get it tight and let her go. And I got you. It usually only makes it to the wastebasket, but you were within range this time. And you can see from the simulation of this particular case here, later on you want to play with this thing with some of the other devices. This throws it all the way to the wall, so I consider that a little unsafe, so we won't demonstrate. You also play with this one. This is one that was made by Arbor Scientific Actually, you have to put it together, but it works pretty well if you adjust it right. But most of the time, the Trebuchet, and I'm going to go ahead and pause this one so I don't use up CPU, and go back to the lecture here. Go ahead to the Siege of Kenilworth. This is one of the wars. It was reconstructed on for a television program. It first showed up in Smithsonian Magazine, and then Nova, PBS ATN, are responsible for carrying this. They spent a whole summer trying to reproduce this throw here, the range of about 500 feet, and speeds of over 140 miles an hour. But if you see all those little dots on the screen there, that's the path this thing is following. And what I programmed this thing to do is to imagine the mass is back in place on the rope, and just with no friction at all, flying here under the force of gravity. These are all feet, which is appropriate since this is an English production. But as you can see, there's really some beautiful curves and trips. And the main thing that you notice about this, if you're interested in optimizing something, is every once in a while it really flings the thing. Most of the time it's sort of dancing with it, but every once in a while it gets into a phase space where it's going to come up here pretty quickly, I think. So right now it's just the opposite of that. It's very tame, but then all of a sudden, bang, you get these explosive sort of whipping motions. And that's what a baseball player, tennis player, lacrosse thrower, they're looking for ways to get high kinetic energy into something. And if you're going to be throwing, a pitcher has to learn how to use two levers, at least two. More than that, there's another lever right there. All of these things working in concert is what you need in order to be good at whatever sport it is you're thinking of. But you can see it's chaotic. There is no closed form expression for what's going on there. There are approximations that we'll work on, but you can see that this is a real mechanics problem. Symmetry be damned. Okay? So, we'll go ahead and pause this one, and we'll go ahead and look at some of the other things that have happened since the Trebuchet became something for people to build. In '95, no one was really talking about it in this country. But if you go ahead and look, well, this is in England again. This time they're throwing a car, and I mean throwing it. It goes out there 800 feet or so with this very heavy mass there. And some of the history of the building of these things, and basically this weapon was equivalent to, I think, the worst weapon man had made for, up to the time that this happened. When the plague went through Europe, they would run out of things to throw, and so they immediately started throwing dead bodies from plague victims into the castle area, and they all would come down with the plague very quickly, and that would be the end of it. So this is biological warfare of the worst kind happening quite regularly with this device. But in any case, what I'm posing here in the beginning of this chapter, chapter 1 of Unit 2, is that we could imagine that Galileo was, like we are now, very often taking a job working on a weapon system. And I would imagine Galileo attempting to solve the equations, or the motion, or deriving the motion for a trebuchet. Well, we all know what Galileo did do, and that was look at pendulums that were made by lanterns in a cathedral, and he was very famous for working out the basic ideas of pendulum, some of which we've looked at already. But the question is, you know, why wouldn't Galileo be able to do that? As smart as he was, and you have to realize that's a couple hundred years of mathematics is yet to be developed. The whole idea of having a differential equation to solve, however numerically or whatever, is a long way away from that time. But we go through each development that we'll do, sort of musing about the possibility for Galileo to actually do a crazy thing like that. Now, see if there's anything else that I need to mention right here. A little bit of more of the history. We might as well show it right now. And that is after about, this is 1264 to 67, it was a very long siege of the castle of Kenilworth, not this castle, but another one somewhere else. And they finally got the thing to work well enough to knock down the wall and to take over and that castle. But at about 1500, on the South American continent, there was Cortez sieging the Indians, Montezuma's people. They'd all built fortifications and were hiding from him. And this is something I call Montezuma's Revenge. Let's go ahead and run it here. They build a trebuchet just in the wild, and the first shot came down and destroyed the trebuchet. That's the story anyway. Okay, now I've talked to historians, some say, yeah, that's what happened, others say, it's doubtful that they were able to even make such a thing, because, you know, you don't have the tools to make the one that, like the Kenilworth one. But this is 200 or so years after the Kenilworth thing, so you have to remind what had happened to build the Kenilworth one. What they went around to do, you need a very heavy weight on a trebuchet. Even this one, this lousy one here, takes a pretty heavy weight to work the thing. You can see the monstrous things that are going on in these contests where they are trying to throw a pumpkin at 240 miles an hour. But what they did was they went around to all the churches and took their roofs off, which were made of lead, and they piled that up and melted it. In the reenactment, they used lead too, but they didn't take it off at church. They bought it, honestly. And the other thing that they did that was kind of new was they had a stonemason make spheres, all of the same shape and size, the spherical shape more or less, and the same size. They ground them down the same size so that they could calibrate the thing. That is, you're always throwing the same thing, and you can make adjustments to get the range to the right thing, right position. Now, at the same time that people were attacking castles with trebuchets, the castles were building monstrous trebuchets, things that had 30 tons in their counterweight. And so they could throw stuff at a much bigger range, and if somebody was building a trebuchet out there, they would target them. So that was the defensive part of this. And all of this being done without differential equations, right? Calculus, all that kind of stuff. Even good algebra hadn't really been developed yet. In any case, I like that story, even if it isn't true, that particular part of Cortez's sinful operations didn't get completed. Anyway, the other things that I would like to point out, besides the fact that we throw them, is that, as happened in history, trebuchet is replaced by higher tech. So if you go out to the Oklahoma pumpkin chunking, you're going to see these things along with the trebuchets, and these cannons, these air cannons. There's a lot of people here that don't have anything else to do, right? it's kind of tells you something about our culture. We need to get people so they can use bigger parts of their given brain. Anyway, this is a monstrous piece of machinery here. Guys wearing helmets, managing the thing to go 4,000 feet. They haven't quite gotten to a mile at the time this was written. I think they surpassed that now. And Halloween's coming again. We've got pumpkins left over of Halloween. These guys come up after Halloween to dispose of the pumpkins by throwing them 4,000, 5,000, whatever feet. So that's the situation that exists as far as the experimental part of this really very strange activity using these devices. But what I want to point out to you is, think of what it took to build our culture. And we're talking tens of thousands of years. Okay, what did it take? Okay, if you wanted to chop down a tree or split some wood, assuming you knew how to make a fire, okay, you needed something to do that. You needed a piece of something that added some kinetic energy to chop or split, or just to cultivate, just to dig the soil. Okay, and then finally, when you got your grain fields working, you needed to do this. This motion right here is a trebuchet motion, 2 levers, very simple motion. Okay, it's kind of the golf swing and tennis drive, and that's the real point I'd like to make here. Is this is in our blood. Okay, it's something that a lot of people can't do. Now, this is the most addictive sport, and I can verify this is probably the second most one. I'm showing 2 motions there that are really important in tennis. Okay, but baseball, lacrosse, I don't show lacrosse. Oh, yes, I do, right there. Okay, the dynamics of 2 levers, the relative position, and all of that is what we're going to be talking about. And understanding that, even something as simple as just going to the county fair and ringing the bell, right? If you know how to do that, you can be a 110-pound lady, woman, girl, and outdrive that 300-pound guy with, big muscles. Okay, so there's a trick to this. And you have to realize that these people couldn't go to the orthopedic surgeon to fix, say, reaping elbow. You got to do it right. Okay? Millions, billions, trillions of times. How many times did somebody swing a reaping scythe, to get us where we are right now? Okay? You have to have some respect for, what happened to bring us here. Here we on this, nice little room here. Okay, well, that was built by people doing that, right? At first. Now you do it with machines. So I want to let you see that this is what physics is really about in some sense. So we're going to be taking it on from the point of view of some algebra and how the coordinates of this thing work, and that's what that's the part of this course that I'm selling you right now. So we're basically going to start off with the very simplest trebuchet, no wheels for it to advance, and that's really surprising, the fact that when you throw with a really big trebuchet, you gain a good deal just from having it step forward, which it does very nicely with a big heavy weight. And of course, when a pitcher throws a ball in the national, or in Razorback, or whatever, anybody really knows how to throw a 100-mile-an-hour ball, that's really quite an impressive thing to do. But they can get an extra 5 or 10 miles an hour, maybe more, by translating. So it's an extra degree of freedom we're not taking into account here. We're just trying to do it with 2 angles. Okay? So we've already done polar coordinates, so we got this pretty well handled, right? But we got an extra polar coordinate system up here, right? So that's what's going to make this a hard problem, much harder than the ones we've considered already. And anyway, it's important to see how you do a problem like this with as much efficiency as possible and with as few errors. And one of the ways to do it is sometimes to use minus angles. That is, this particular angle here is moving the thing in a clockwise direction. So I stick a minus sign on that just to annoy myself well enough so I don't make a mistake. I get the minus signs in the right place, and I make sure that I have a distance that is, this positive distance is minus r sine theta when theta is negative. And let's see what else here. This angle here is the same as this angle right here, similar triangles. Okay, and it's the same as this angle for the big black triangle that's holding the major portion of the lever that's going to do the throwing. And then for the moment we're imagining just a very short length of the string right there. And you come up after class, we'll put a short one on here and see if we can get it to the wall. But the angle for that one, we're going to give it as a phi. Now this one I've taken a positive value for it, that is, I'm imagining a right-hand rotation for that. So this geometry here is being simplified right there. And that's what's giving us a set of coordinates for the mass we're going to throw. The driver with an uppercase M to indicate it's larger is going to be giving its kinetic energy as much as possible to this little guy whose x and y coordinates, and we're using this as the origin, so the x and y there, that is the key thing to getting those. And then once we have this from theta, we also have x and y coordinate to add to that due to this angle, phi, right there. So that's the key starting thing for this that you would be making if you're... Oh, and obviously what we're making here is a differential equation to go onto a computer. But we're going to play with that differential equation, and we're going to do some more funny kinds of coordinates, including, we haven't done Riemann equations yet, so in the next lecture we're going to touch on those. Okay, let's see if there's anything else I need to point out here before I load the screen here with stuff having to do with the Jacobian of this transformation between the Cartesian coordinates big X, big Y, and little x and little y there. These two coordinates right here. Okay, so go ahead and keep these more or less up to date here. There's the real equation that we're looking for there, and there's another way to look at that equation geometrically down below there. So that's really all the geometry there is for this particular system, the way it's being shown right now. Now, Jacobian, that's what we need to start off mechanics. We have the big X and big Y. That is just our original polar coordinates that we had before, and now we're going to do it again with some minor changes associated with having different signs there, but that is where we go to get the differential relations and the Jacobian that we need to solve this. Okay, so there are the differentials, and those differentials have a raw Jacobian. Okay, the idea here is we have only two angles that we really care about. We're assuming this thing is constrained to stay on its bearing, That's no mean feat. This is the hard part of keeping the trebuchet from just falling apart with tremendous amounts of force involved in these objects. But right now we're assuming it can handle it, and therefore we only have 2 degrees of freedom, little phi and theta. Okay, but we've got 4 coordinates. Okay, 4 Cartesian coordinates. So we get a rectangular Jacobian. That's something we haven't confronted so far, right? That's just sort of a stopping point at this juncture to handle that Jacobian. So the question is, which or if any of these components right here, namely these, are going to get me out of this jam. I've got to get a square Jacobian. I've got to have something I can invert, or forget it. So that's the first hang-up to doing classical mechanics, is getting over this. And no problem when we did the polar coordinates, because we already know what they're. But this is the one that's got 2 polar coordinates in, so how do we handle it? So if I just try to use these guys right here, I'm in trouble right away, because the determinant of that, 0. Okay, it's always singular. No, you can't use it. That's not any good. So we go on, maybe try this one and this one, or this one and this one, or something. Something's got to work here, and you probably can spot for yourself what it is that we're going to need to do here in order to get something that's going to work for us. And so, see that down at the end there, at least what looks like a fairly reasonable choice for a square Jacobian that will get us started here. And all we're accounting for right now are the differentials of little x and little y. We have to superimpose the simple polar coordinates that have to do with the big theta, but this is going to take care of the little x and the little y that involves the thing we're throwing. The thing that's driving it is going to be added shortly here, but this is the one. This is what we have to do in order to get this thing to work. Now this thing isn't always non-singular. It's usually non-singular. So we can say that this is a successful choice for a Jacobian to take us to the mechanics. All of the Lagrange equations and all that kind of stuff we're going to derive today. Got to get this first. That is definitely a part of the order here, because we need to have this to be a relationship that involves the velocities. That is, the velocities of x and y, or the angular velocities, have to be related. And remember that lemma 1, the same relation applies to them. So that's where we stand as far as getting started on a mechanics problem, is getting it to the point where I can write a Jacobian, the transformation from Cartesian to some sort of generalized coordinates. And these are very generalized, non-orthogonal coordinates that we're talking about here. Okay, now, before when we had qualifying exams which made you do this in a hurry, we don't do that anymore, okay? People will actually look at we discover people look at all of the universities when you apply to graduate school, and if they say they're going to have a qualifying exam, you cross it out. So that's where we stand now. So you don't need to tell you this, but this is what you do is something to make sure that you've gotten this far without making a mistake. You try this thing out for various singular, you might say, but identifiable positions, like totally folded up, or just sitting there in its state that would be before you cocked this trebuchet. That would just be the rope hanging down and things straight up. That's the equilibrium position. You check to see that you're getting the right values for various things. And this one, and this one. This would be an important one, because that's going to be the point where, we'll explain it later, you've ceased to be putting energy into this thing, you're simply steering it now, if it's close to perpendicular. Anyway, that's something that is recommended for making these things an arithmetic. And you'll get some problems to do that you can do at home. You don't have a time limit, so you really could ignore what I'm telling you right now, but obviously you want to save time. That's a good thing to do, is check it out. See what you've got. So anyway, when we get to this point, where we have something we trust in terms of a Jacobian, and relationships between the big X and big Y and the little x and the little y, so as soon as we have those relationships, we can begin to make the Lagrange equations for this particular guy. Now we're not just making them, we're deriving them. So we're redoing all of the stuff that we had to do in order to get Lagrange's equation. We're doing it now with a non-trivial device. Okay, so the way we're going to handle this, and I think this is probably important for as we get to more complicated things, is we look at both the Jacobian relationship, and there's one between the little coordinates that involve the projectile, and well, writing this thing this way and this way lets us write in a very nice way a quadratic form. So right now I'm at that stage in the first lecture when we talked about quadratic forms being some sort of mass thing and some sort of velocity squared thing. So we're going to make an equation that uses that as a way to, let's see if I can get started on these right here, which show what I'm after. There's the basic Cartesian coordinate system for the, or kinetic energy for the projectile and for the driver, and the way to make that useful. Now go ahead and get ahead on this one as well. To make that useful, I use both of these relations. In other words, this thing and then the transpose of it. So Jacobian and JT is the transposed Jacobian matrix. And we're going to write the kinetic energy as a non-trivial quadratic form. And that's a key way to have a decent set of bookkeeping that doesn't let you make as many errors. It's a shortcut, a little bit of a shortcut, is to write this kinetic energy. Now this involves this just for the projectile, but we've got to add this as well to that kinetic energy. So there are everything's accounted for, but it's not accounted for yet in a single equation. We do need to put these guys, glue these two together. Two completely different masses need to be glued together, and this is where it gets a little tricky. We never have talked about, except for the superpoles, and those are just episodic collisions. Here we've got something where they're going to be playing with each other in different ways throughout their motion. So we got to get this thing in there as well. So this one involves a theta dot squared, so it's going to just show up right here as one extra term in this quadratic form, but it's an important one. So now we've taken care of both masses, the little mass and the big mass. That's the Cartesian equation. Here's the quadratic form that gives you what you're after, the kinetic energy T function. T for kinetic, I guess. All right? Okay. So we've gone from the raw Jacobian to this. That's what has happened in just these last few maneuvers here. But as I said, we're going to, from this, derive the Lagrangian equation of motion. Lagrangian force equation of motion is what we're after. Okay, let's make sure we have all of the stuff that I need to say here. So that's just connecting each of these pieces. Okay. Now, the reason I'm being careful with all of this is because I need to very carefully define this thing we call gamma before. This is a dynamic mechanical metric thing. It has the same general properties as just the length, space, time, and gravity, but in any sort of space, we have a g mu nu. Well, this is gamma mn, and it's going to have masses inside it, hiding. And that is not standard practice, but boy, it sure helps for things like this. So I'm selling that right here with, you know, I'm being serious about this. We're taking this metric and we're going to transform that metric into the degrees of freedom coordinates, theta and phi. And that's a non-trivial step. It's not one that you see in most of the mechanics books. In fact, I can't think of any but my own that really does this in the way we're doing it here anyway. So anyway, we've got this kinetic energy function. It was Cartesian, now it's in angles that we're velocities and angles that we're interested in. And it has this form. This is the gamma mn. Whatever it takes to take the coordinates, velocities, the coordinates, and the velocities, here theta and phi, and then theta dot and phi dot, to take that, and that means this thing has to be a function of theta and phi, and then this is the only dependency on the velocities that we're allowing here. If you have more than that, you've got some other work to do. But remember, the Lagrangian stuff depended on having the Cartesian coordinates with the coefficients not being functions of coordinates. In other words, if you walk over here, I don't want to be heavier. That's a whole different problem. That's a different. You have to treat that problem differently. Okay, it means you're in a field of some kind, and so you got to go back. But if you can write it this way, in other words, if you can write the gamma matrix as opposed to the G matrix, well, we're on our way. Now we can do all of the Lagrangian trickery that's needed to make a Lagrange equation of motion out of all of this stuff. Okay, so let's make sure that this is on all three screens here, and it makes sense. So there's that product, JT and J. Which one you call J and which one you call JT is kind of lost, but be consistent. All right, is this making sense for the most part? Okay. Well, the structure of that is very key. So I'm noting that this particular kinetic expression for the driver and all of the other expressions that involve the projectile are together in one matrix, one JTJ product matrix that we call the dynamic metric. And we're going to treat that thing like a metric for the most part. The covariant and contravariant stuff will come. Now, as you probably have noticed, the chapter 2, I'm sorry, unit 2, the chapters in that unit don't make a big fuss about the tensors and the covariance and the contravariance. This is all redone in the unit 3 with that covariant, contravariant stuff. The GCC stuff really is taken seriously. What we're going to do in these lectures is do them both at once. Okay, so in the next lecture we'll make more of a fuss about the GCCs, but we'll still have this thing to deal with. It will be our geometric G, but it's got kinetic physics associated with it. Okay, let's see if there's anything I need to say here. This is the expression written out in sort of the Gibbs notation, just to make clear what it is, that connection. Let me go back here and point this out. In general, we're going to have quite a number of masses, especially when you get to talking about wave phenomena, mechanics of waves in a lattice, for example. We're going to have quite a number of masses to sum over in order to make one of these kinetic energy expressions. But basically it will boil down to having the velocities related to queer velocities, Q velocities, these general GCC velocities, and a transformation matrix that is transforming us from the Cartesian to the Q coordinates. Okay, so this is, you know, the end-all and be-all for any mechanics. And we're at the moment going for the Lagrangian stuff that is a function of velocities. So that's how it looks like when you write it in code. See if I've got everything here. Anyway, again, check it out with special cases. Special cases are really important for doing this. I'll leave the algebraic expression down there for the moment. And try it out for completely folded up. This is almost what the trebuchet starts with. You saw when I had the lever all the way, almost all the way down. I mean, it was a little bit below. But we put the mass not inside the lever, but below it, just a little bit below it. And then it's going to fling the thing. Okay. This particular setting here, you start going, unless the gravity drops the thing for you, this is never going, you know, in principle, never going to leave when it rotates. The centrifugal force is not going to tend to drop that thing, so you have to watch out for it. Now this is where it's at the point which we call the aiming point. We'll get all that stuff later on. And now the expression for it, instead of being r minus L squared omega squared, it's r squared plus L squared. That's the hypotenuse, the radial arm to that mass. We're just checking the kinetic energy of a little mass. This one's easy, but this one's the one that could be tricky. So that, again, is, as I say. And then finally, the release point. The release point is where it's stretched out. Okay, at this point you have hopefully the maximum kinetic energy in that little mass, and you're in some orientation with respect to the thetas that will aim it correctly. And you can pretty well see at this point, just by looking at these things, let's put down here the cases, but just looking at this thing, you can see aiming this thing is going to be tricky. So, go here also. Now, a usual case is the coordinates that are associated with this, that is the theta and the phi coordinates are not orthogonal. Now there is a brief moment in every one of the trajectories probably that this is orthogonal to that. There you actually have a brief instant where the coordinates are orthogonal, and the off-diagonal matrix elements here will go to 0. So in some senses this behaves like a metric tensor that you do for just pure geometry, analytic, I'm sorry, differential geometry. Okay, so that's where we stand as far as making kinetic energy things. Now, let's do Lagrange's stuff. If there are no questions about what we've got so far here. Okay. I want to lay this out very clearly, because remember, the thing that we have here is a little different from when we introduced the Lagrangian for just a simple polar coordinate system. In that case, there were a radius and an angle, and then there was an x and a y. No problem, okay? Here we've got something that involves coordinates that we're interested in eventually, which are the thetas and the phis. We've got 2 of those, remember, and the raw Jacobian is not square because we've only got 2 of those, but we've got 4 of the Cartesians. Okay, so here's where the arithmetic associated with building the, in this case, the work differential that you started off to get Lagrange's equation is different than what we did with just simple polar coordinates. There was 2 to 2, here it's 2 to 4. So we have to be a little careful with having 4 here and only 2 for our theta and phi, which we're about to use the Jacobian to produce. Okay, but this is the raw Jacobian, not immediately in a way that we can handle it. So we have 4, and then we're going to have 2 when we write all this out in the degrees of freedom that we've chosen for this mechanics problem. Okay, so that is a key to this, is we've got to learn how to handle that. How does this transformation work when it's got 4 things on one side and 2 on the other? That could be a little bit of a headache. Well, if those 2 are golden, so to speak, that is, if these are the variables that are the independent degrees of freedom, if that's the case, then we can do something that makes this have some sense to it. So start with, these are independent, so I'm just going to make the differential d phi 0. I'm only going to work with theta. Okay? If I do that, I just get this. I just get this part. I turn that part off. Okay? And then I'll do the other. I'll do the other end. Okay? So we'll do these as separate entities. Each one of them has a Lagrange equation associated. Very different Lagrange equation, but this is the way to look at it. And that 4 transformation, 4 by 2 transformation is part of this deal here. Okay, so what to make of that? Well, remember the first step of the Lagrange trickery, besides axiom 1 and axiom 2, involves this little time derivative of something, something with we just call x here, but also u is this guy right here. Okay, the derivative being that. So we write that out. This is a time derivative of this thing minus this thing. That's what's where the Lagrange trickery that we talked about before. And lemma 1, that's what I should have called it as lemma 1, not axiom 1. But lemma 1 and 2, these are all from that lecture 9. Quite a few lectures to go. Here we are at 14. And this guy and this guy are being used. Lemma 1 is turning this thing into this partial derivative of x dot with respect to q dot is exactly equal to just the partial derivative of x with respect to q from the original Jacobian. Velocity Jacobian, same as coordinate Jacobian. Okay. Now when it comes to doing double derivatives, there's a time derivative here and then there's a spatial derivative there. That turns in by lemma 2 to the derivative of a Jacobian component. And we just do this for each of these pieces down here. Okay, and then step C is to just make a Lagrange form. Okay, there's the that u that is the partial x with respect to theta or y with respect to phi. Any one of those factors part of the Lagrange form. Okay, so that's a key step. Okay, now we do it for everything. And this looks like sort of verbose and maybe unnecessary, but this is how you take this generalized approach to Lagrangian mechanics apart, just to see what it is that you've got. Because what you're going to have here when we're done is this sum of things here. It's 4 things, but we're trying to reduce it so it's just two things, and that is the main trick of this Lagrangian setup. So, add up first and last columns for each variable is basically the idea. First column, last column. Okay, first column, last column. Just add them all up, and you get something that involves the Lagrangian form of a kinetic energy. So basically, the kinetic energy come to us in Cartesian form with four things collapsing. This is where the collapse occurs and where we get what we're after, and that's the Lagrange equation for the theta. And just another step here, you get the phi. Okay. So that's it. That's the end of the Lagrangian trickery. We now have everything in terms of the GCC variable phi, everything in terms of the GCC variable theta. We did this immediately with the polar coordinates, but we've got four Cartesian coordinates here, now going to two polar angles. One for the driver, one for the projectile. Okay? So that's it. And of course, if we were going to just do French stuff, Lagrange stuff, okay, it's the hardest as it gets. Now, force equation is all we've got. It's true, we've got the force worked out. We can write it as a combination of all of these partials, and that's what's weird, is that this involves four terms. So when we write this thing, that's what we mean, that sum right there. And this thing has four things hiding, not two, but four. So this is where you change dimension, collapse a dimension or two. Okay. So this thing and that thing are what we're working with, and it contains whatever its Cartesian birthplace demands it to have. Okay. Well, at this point we can go ahead and check out the various forces that you could imagine having to deal with if you just went at this thing using Cartesian coordinates. And that I'm going to rush over that. That's something that would be important if you want to make sure that what you've written so far is correct. You have competing signs and things here. Torque for the throwing lever is pretty obvious, but for the those two, we have one thing that's defined with a minus sign, another thing with a plus sign. Is that correct? You see. Are there plus and minus sign errors here? You see, that's the thing that can throw you. One sign in this business and you're out of business. So it is really important to take these things apart for special cases. Even if this would be a case where I might want to try theta when it was 0 and see what happens with my phi and so forth. So this is a stopping point before you go and waste all your money on a computer program that's going to simulate a piece of garbage. You got to make sure this is not garbage. And that, of course, is not an easy job. Okay. And the answer to this particular question about the signs is no. The beam is in a minus theta position, so that sort of checks it out for that particular thing. But there are other things in there that you need to look at before you go and actually do something with Lagrange's force equation. And the first thing we want to do is get it to Lagrange's potential equation, but we also want to see what role the metric tensor plays in our equations of motion. So once again, let's go back and look at the total kinetic energy in terms of the GCCs, theta and phi. And there is that, that's what we're dealing with there, and it's got the driver and the driven projectile all in one place. So if we've been careful, we do have here a generalization of angular momentum, a very queer one. It's Q business here, okay? These are the GCCs. This is a piece of theta, that's the driver angle, and this is a piece of phi, that's a momentum associated with the driven. So that's kind of weird, and there's what it is if you write all the pieces out. Okay? And what's neat about this is that this P theta and P phi are being written here in terms of velocities. Okay, so what's happened is we've taken a metric that has, I'm not supposed to use these words, but covariant and contravariant, in this case covariant components, and then we're working with a velocity here, and you know velocities have their indices up in the air like the contras, right? This is a contra quantity, these velocities, and we're ending up here with a covariant quantity. Now, we wouldn't even mention that if we weren't making use of Riemannian geometry. Gauss, Riemann, a bunch of mathematicians built tensor analysis. The fact that this happens this way, this partial derivative phi with respect to velocities, gives me momentum without much fuss, as long as I'm willing to adapt these gamma as opposed to G matrices. And you see it has two kinds of mass in it. So this is a dynamic metric, a tensor that we're playing with here. Now, there's a quick proof that this is working that I would point out to you here. That's getting a little bit ahead of us there. But I'll make sure that I have all the pieces that I need right here. Yeah. So that last result down there, that's the first example of using dummy sum rules. Okay, this is the way we would write it in tensor analysis when we get into the Riemann world. That's what this becomes. Okay, and there's the momentum equation right there, just in terms of each component, however many there are, of the GCC coordinate velocity system. And when you take this sum and expand it, you get a half and a half, which adds up to a single value, namely, with the delta functions here, this becomes that. Okay, gamma matrix times the velocity. So on each of these, I want to make sure that that's clear. Okay. Now there is a quicker way, maybe quicker, but it takes more paper to do this sort of tensor analysis. I point that out in the middle. I'll use the middle screen here to do that. This is the matrix there I'm writing out. You just write the thing out as a big old matrix like that. Take partial derivatives in the components, add them up. You get a half plus a half again, and that's the result at the bottom there. So these are two ways to handle these things, and I want to make sure that that's clear. Now this is hard to display in the text, so the layout that I gave you isn't in the text. That's what lectures are for. They're not totally useless, right? It gets a chance to write things in funny ways that you can't do in a textbook. Okay? All right. Let's see if there's anything else I need to say here. I think that's pretty much it. Once we've done this two ways, that's another thing about doing it two ways, is to check the tensor dummy sum rules and all that kind of stuff that you might have screwed up. The matrix won't have that problem. But anyway, look what we've got here. This is time to take stock of what it is that we're able to handle. The number of constraint forces, and they are not small, they're huge for a trebuchet. the number of constraint forces, for example, there's a two-dimensional one there. I don't even know what direction it is at any moment. There are all kinds of, this force really counts. This is the gravitational force. We're going to have to take care of that. We're going to have to take care of, for this one, definitely put that into these equations. And that's this thing that has 4 terms, remember. So we're going to still have to do that. But this thing is moving fast, so it'll be a centrifugal force. It's proportional to theta dot squared. There'll be another one that's somewhere in this direction. Okay, and then of course there'll be a constraint force that's got to be in line with the rope that's holding the projectile. And then there's a Coriolis force that's proportional to the product of velocities. There's just a mess here. But we're taking care of it with these 2 equations. You see, this is the magic of the Lagrangian deal. You see this, all that stuff can be ignored. All the constraints, beautifully ignored. Now, that's going to be a major part of our analysis as we go into the geometry of, well, what are the constraint forces, right? If you're an engineer building this thing, you don't want it to collapse. You want to know what's the maximum this thing gets to, right? That's the hard part. Oh, but we can do that too, using this type of formulation. Okay, now, what if those forces, and I'm talking about those 2, are the only ones we have to worry about. Forget all the others. What if they could be written as a potential? That is, a physicist potential, minus a gradient. Okay? So each one of these coordinates, and the other thing that has to happen in order for this trick to be pulled off, is that potential cannot have any velocity dependence. Okay? That's going to screw our for magnetic forces. So we're going to have a separate derivation to handle magnetic forces. Because you very much are a function of velocity when you're doing your B cross V, right? As long as I don't have anything like that from my potential, and I can ignore that, then I've got this. That's what happens. This thing turns into a derivative with respect to just angles, theta and phi. Okay? So then, that's the last Lagrange trick, is to write Lagrange equations this way. Now remember, they're really pretty much the same. To get this one, I take the dot off of this one and put it there on this one. And then, of course, I do it for all of the generalized coordinates that I have. I only have one more. So if you want something that's easy to remember, and that's still the case. I mentioned it with the polar coordinates, right, of just one mass, but it's true here now, too. Okay. So that gives you a little bit of confidence for dealing with things like this. Okay, so we're pretty well through just taking care of the French side of the trebuchet, which is appropriate because trebuchet is a French word. Okay, all right. Now, we've got a few more minutes here. I want to point out the multi-valued trouble with this coordinate system. And to do that, I want to point out that polar coordinates really had this problem too. I think polar coordinates are without the z's. Well, they've got a disease just like our trebuchet. Okay. And that is, here are 2 completely different configurations with the same x and y. It's double value. Coordinate system's double value. This is a big deal for people that are working in quantum mechanics. It's also a big deal for the trebuchet. Okay? So we need to have a 2-sheeted coordinate system to really make this thing have the proper topology. Now this is pointed out right away in the beginning of Unit 3. We don't get to really fuss with it much in Unit 2. But remember, as you go through the origin on a polar coordinate system, you come out the other side. That means you come out on a sheet below it. So even the polar coordinate system that we said was so simple is not simple. Okay, well, that's a little bit of warning there, all right? This is kind of what it looks like. In fact, it's pretty much exactly what it looks like. You end up with a torus as the topology for this. Now what I'm going to do, I'll put this particular picture on that screen, but on this screen, what I want to do is I want to switch projectors for just a minute here to the machine that should be working here. Let's see if it is still. Yeah, I think it is. It's sort of blinking, coughing, and sputtering there. Let's see if it's going to come up for me. And this is something we don't have in our Trebuchet program, so I have to bring it up here. And maybe we do hiding somewhere, but let me get this.
We do, but it's not very functional. It's just like showing pictures.
Yeah, because in order to demonstrate this, I have to get the thing working. I thought it would stay going for me, but it blinked out. And we go down here, get everything working again here. I'll see if I can get the detect displays to tell me everything's okay. Blink, blink, blink.
There it is.
There we go. Okay. And then one more thing to do here. Get this app up and running. Means I gotta get that. And that's going to be hiding back. There it is. That's what I'm after. Okay, so when I draw, and I think that's what I want, is a typical Trebuchet coordinate system. You should be aware. Go ahead and sit down here so I'll get my mouse in the right orientation. If I go up here and just pick a coordinate intersection right there, and then go ahead and move it. You see, this would be a case of I go from Trebuchet that's completely locked up to one that's completely open, and it's a left-handed Trebuchet, right? Your fingers bend this way on your left hand, not the other way, right? Underneath that is the other sheet that's kind of shown up there, okay? Now when I go to, say, this particular point right there, I want to be actually right there. Well, that's good enough. Anyway, as I go with the angle theta, I would be on one of the trajectories that are green, okay? It continues on the other side, okay, that circle does, but only this part is valid, and I should put the thing back so it really is on a particular point there, and then put it again, say on this point, and then go ahead and make it go on that. See, that's a legitimate coordinate for this sheet, and if it were to continue down there, it would be about to there, and then it's not legitimate anymore, you see. It's on the lower sheet now. It's on the right-handed sheet now. That's a right-handed Trebuchet position, right? So this is the way you psych out these weird topologies for these multi-valued systems that you'll see this more in quantum mechanics than you will in classical, but there it is from the 10th century, okay? It's really old, right? But it's still got this amazing topological property that we have to work with. So we're showing both sheets in that diagram there, and at this moment this one is operating with that particular theta, okay, and then the phi, this particular phi equal a constant over here is operating from here to the equator, the inner equator of the top of the torus, from the outer equator to the inner equator, and then it continues on the lower surface to finish that circle but you don't draw that up here, you draw that down here, you see. And that's the way you sort of analyze the topology of this thing, just by waving your hands. I mean, it's a hand-waving argument for the topology of this peculiar instrument. Now, as I say, left-handed sheet, right-handed sheet. It's best I can do, I'm giving it a name. The other thing you can do, and this is something I'm asking you to do with some of these coordinates, is you have a coordinate system Q1, Q2. Just plot it as though it was Cartesian. That's what I'm doing here. Okay. So this program actually does that, that I recall, and I think the new one that we have, that you have access to, also does that. And you see, if I've got that position face close, there's the position space. Just with all of them laid out, this one is a little finer, there's a lot more trebuchets in there, but you can see all along this line, the angle phi is constant. Remember, all these, I didn't mention this, but I should have. All of our angles are lab-based. Later on, we'll go and mess around with angles that are based on some piece of machinery, say that lever right there. But you see, all along this line, the projectile has this angle, right? And the other parts of it are following a circle, the green circle, corresponding to the theta. Okay, so it is plus 90 right there, okay, and then phi here, okay, is, and then there's a dividing line, the equator, you say, the inner equator and the outer equator. So these are the things we have to worry about as we build our geometry. In other words, as we build our covariant or contravariant. I'm not showing any of the contravariants in this particular thing, but the covariants are the ones that line up in the tangent. They're the tangent space. This one tangent to that green curve right there. This one tangent to the phi, this curve right here, the blue. Okay. So phi's all constant here, 0. Phi's a little higher right there. And then as you go down the line here, the thetas are all the same. Okay, the position of the main beam of the trebuchet, theta, is 0 there, and then I had it marked here. I guess I don't have it marked here. About 45 degrees or so, and then 90 degrees, and then 135, and so forth. All along there, then along there, and so forth. So that's just a I don't know what you call this. This is a chart. It's not a manifold that you can trust your calculus on, but this one is. And it's 2 of them. You got to have 2 of them. Okay. Well, these are things that we'll be talking about more later on, because we do need to make covariant vectors and contravariant vectors and all of that stuff. But that's fairly trivial. It's not much more difficult than just the polar coordinates, just to make sure you're working with the right angle, theta versus phi. So we'll take this up on the next lecture as we go deeper into these tensor analysis, I guess, or topology, or whatever you want to call it. It's a mixture of all sorts of different mathematics going on here. But that's physics. That's what it is when you get right down to it. Okay? Any questions for them? You know it all. You're ready for the exam that's coming. You guys have been doing real well on the homework, so I'm going to hold off on the exams. Tell them to keep doing well on the homework.
So it's 2 half toruses with like a different handedness?
If you call a half torus something that you could drink out of,
yeah,
right, and then there'd be a top to it, okay. You're right, yeah. The right-handed and the left-handed, yeah. Right, which is not obvious until you look at the actual markings on the thing that's indicated in that attempt to draw the 3D. Yeah. Anything else? Good. Okay, we'll see you on Wednesday.
Actually, I do have a question.
Oh, go ahead.
As I think of them. So what's the actual equation that you would plot to make these simulations? Does it have all four of those terms in it?
The equation that is needed is a solution to the differential equation.
Right.
And so all you're plotting are the values of phi and theta. That's all you do. Now you convert that back to x and y if you've got an xy coordinate system for the computer, but very often you're working with some of these fancy graphics languages you do have. You can make the theta and phi be your variables. I think Python does that. But our programs use x and y, and then get the theta and phi from the differential equation directly. That help at all?
I guess, I mean, what is the actual differential equation? It has those four terms?
The actual differential equation,
The advanced Lagrange.
we have
With conservative.
kind of have it already here. Let's just go ahead since you asked. The actual differential equation, that.
It's systemized already.
That's it.
With the t minus v?
Yeah, yeah.
Okay, what's v? Just mg?
Gravity? Yeah.
Well, we do have
It's touching
an
two
M-
places.
Or two
mg,
different...
and you have to make sure that that potential is in there. Okay, that's definitely part of the story
Cover
here.
your question next.
Yeah. But these are the main variables right here for the momentum.
Very good question.
Okay. Now what you have to do is we have a relationship right way back at the beginning. Way back at the beginning we have, let me go ahead and take this guy back to this one. I think it'll show up fairly quickly. Way back at the beginning we have the equations that give you the actual x's and y's of the objects in question. So if you had an xy plotter and you would let your differential equations give you theta and phi, you would be plotting these two. That would be for the little guy. Then for the big guy, you'd just be plotting that and that. So if you've got a simulator like a Mathematic or something, you can take everything we've done here and put it in a Runge-Kutta, or you can just ask Mathematica, here's my differential equation to solve it, right?
Right.
And plot, and I mean, but if you've got a more primitive mathematical program, then you have to work out the relationships that give you little x and little y and big X and big Y after you've found theta and phi. Now, when we do the Hamiltonian, that Runge-Kutta is automatically. So if it's a Runge-Kutta that you've got, you feed the Hamiltonian into that. We're going to have to talk a little bit more about that in the following lectures. Or you get real fancy and we do the Riemann equation. That can be set up in Mathematica very easily. No problem with Riemanns anymore. So there are a whole bunch of different equations that we can be writing here, and we'll do that Riemann a little bit next time, and then following week we'll take that one on. But that's the one you're going to, if you're going to go into gravity, that's the equation you're going to use for mechanics, is Riemann's. Riemann's monster, and that is, if I can get this thing working, there's the covariant Riemann and there's the contravariant Riemann, and the contravariant is one most often used. So we'll talk about those guys later on. The problem with the Riemann is you can't have explicit time dependence. How do you get out of that problem? You make one of the coordinates time. Now you're in 4 space and you're doing relativity. So that's why Riemann becomes powerful. And we had that power demonstrated when we had that wonderful and the black holes collapsed. That was a hell of a lot of Riemannning. Okay?